Hi there, folks. Today we're looking at exponential functions, and we're just going to look at these from the most basic level in terms of graphing and how they work and how to identify them, the patterns that they hold, that kind of thing. But an exponential function, the defining characteristic here in terms of the equation is when x is part of the exponent, all right? The variable is in the exponent, all right? There are other function types that we'll look at that have exponents in them, but they're numeric exponents. An exponential function, the variable, the unknown, is part of the exponent, okay? So exponential functions, they're in this format of y equals a times b to the x. And, when it's all said and done, a and b will be numbers. The variables will be x and y, all right? So x, the input, is the exponent, all right? And the output is what we get from the result of that exponent, all right? There's a bunch of little stipulations down here for exponential functions. It's in this format, but a can't be 0, and b has to be greater than 0, so it has to be positive. And b can't equal 1, and it has to be real numbers plugged in here. So there's a lot of little stipulations, but just to break these down, and these aren't super important as we get into this right now, but if a was a 0, it kind of wipes out the whole function. Then it's just y equals 0, which is a horizontal line, all right? And that's why that one doesn't work to create an exponential function. The b value having to be positive, that's because if the b value is a negative, all right, as you plugged in different x values, sometimes you get positive and sometimes you get negative. So the pattern kind of breaks down in terms of the graph. You're jumping back and forth between positive and negative for your y. Doesn't work, okay? And then if b is a 1, well, if you have 1 being raised to a power over and over again, it's just 1. So then all you have is y equals a times 1, which is y equals a. And once again, we're back to a horizontal line. And that's why these little stipulations exist, okay? By changing those values, if we used a values of 0 or b values of 1 or b values that were negative, it kind of changes the function so that it doesn't follow an exponential pattern, okay? It changes us to something else. And so, again, those aren't super important right now. They're not going to really come up that much, but we just want to get the general format for this thing, all right? For example, if I look at something like this guy, this is a really simple exponential function. It's y equals, it's in the format a times b to the x, but y equals 2 to the x. If you wanted this in the true format, this is like times a 1 out front here, so we could rewrite it and say, hey, this is y equals 1 times 2 to the x, okay? So keep in mind, just like with other functions, we're going to have invisible ones kind of hanging out in different places. Now I can see the a and the b value here. And I've already chosen x values for us. We just have to plug them in. And be careful, negative exponents, if I plug the negative 2 in for x, remember negative exponent, if I'm trying to do this, negative exponent flips us, so it's 1 over 2 to the second power, which is 1/4. Likewise, if I were to plug a negative 1 in here, again, a negative 1 for an exponent flips us. It flips the value to the other side of the fraction bar, makes it positive, so this is actually a 1/2. And so just be aware of that. Be careful. We'll use your rules of exponents to simplify. The rest of these are pretty easy. 2 to the 0 power, anything to the 0 power is 1. 2 to the first power is a 2. And 2 to the second power is a 4. All right? And so if I plot these, ready, negative 2, 1/4, probably around here somewhere, 1/2, 1, 2, and 4. So we get something that kind of looks like this. And as we look at that thing, we have a general idea that, okay, this looks like a curve of some kind. It's obviously not a line. I can't draw a line through these, so it's a curve of some kind. And so I could probably go like this and say, all right, I'm going to predict that it's going to kind of go like that. What students are unsure about is what happens at this other end. And if I kept plugging in more and more negative values like negative 3, well, 2 to the negative third power would be a 1/8. If I did negative 4, that would be a 1/16. And you can see what's happening with these values. They're getting smaller and smaller and smaller. We're getting these tinier and tinier fractions. But the question becomes, will it ever go back up? And that's probably obvious. The answer is no. It's going to keep getting smaller and smaller. The next question is, will it ever reach that 0? Will it keep getting smaller to the point that it gets to negatives? All right? And the answer to both of those is no. Okay? It's never going to reach 0. When you think about it, 2 to what power will give me a 0? And there is none. There is no value when I raise a positive 2 to an exponent that would give me a 0. There's no value that would make it negative. Remember, negative exponents here just create fractions. They don't create negative values. And so what's going to happen is this guy's going to keep getting closer and closer and closer to the x-axis, but never actually get there, never actually reach it, okay? And the idea here, this is a concept you'll talk about in Algebra 2, but we're getting towards that idea of an asymptote, okay? It describes what happens at the end of this thing, but a lot of times with asymptotes, we never actually get there. We never actually reach the asymptote, all right? It's the thing we're getting closer and closer to becoming as the function goes off to forever, all right? And so this is an exponential function, all right? This is considered exponential. And look for the different patterns here as you kind of look at the graph. I went from a 1, 1/2 to a 1 to a 2 to a 4. You can probably guess that the next one is an 8, all right? And notice I'm doubling the height each time, okay? So kind of think about those things as we're looking at the patterns from the graph here, okay? If I look at the next one, a 1/2 this time. And so once again, if I wanted to rewrite it so I could see the b value, it's y equals 1 times 1/2 raised to the x. So the b value is a 1 this time again, all right? We're keeping it simple right now. And so I start plugging these values in. And once again, be careful here. If I have 1/2 raised to the negative second power, well, remember the negative exponent flips the thing, so it becomes 2 over 1 to the second power. So just 2 to the second power is a 4. Negative 1, if I do 1/2 to the negative first power, again, I flip it and raise it to the first power. So that's a 2. 1/2 to the 0 power is a 1. 1/2 to the first power is a 1/2. 1/2 to the second power, remember I do numerator and denominator separately, is a 1/4, okay? 1 to the second power is 1, 2 to the second power is 4, so it's 1 over 4, all right? And so let's look at the graph of this thing. Let's see what it looks like. Let's see, negative 2, 4. It's right here. 1, 2. And look at this. And as you're looking at this thing, hopefully you're looking at going, that looks really familiar. I've seen something almost identical to that. Well, yeah, it was the previous problem. Looked exactly the same way, except it's flipped left and right, okay? I even still have the same values. 4, look at this, 4, 2, 1, 1/2. Okay, same thing here, 4, 2, 1, 1/2. Okay, the only difference is the direction that that's happening, okay, as we kind of look at that pattern. And so if we recognize that it's pretty much the same thing, we should recognize that the same thing is going to happen, except in this direction. Okay, except in this other direction this time. We're going to get closer and closer to the x-axis, but won't ever actually get there. We'll get closer and closer and closer. The fraction will get smaller and smaller and smaller, but we'll never actually reach 0. We'll never actually reach negatives. Okay? And once again, we can kind of see the pattern here as I go left to right. I went from a 4 to a 2 to a 1 to a 1/2. You can see the height is getting cut in half, which means working backwards, I could tell that there was probably 8 up here, so this went from 8 to 4. Okay? And so that's the idea here. We want to look for these patterns. The other thing you might notice, so we kind of described the height in terms of that b value, right? The b value is telling us how far we go from one point to the next. It's getting cut in half each time. But then we found the a value in each of these also. Right here. Here's the a value. It's 1. Here's the a value is 1. But then the question is that going to remain the same as I change the a value? Okay? And so the a value appears to be the y-intercept, kind of that starting point. All right? And then the b value appears to be what we change the height by in terms of multiplication. Let's see if that holds up in something like this one. Okay? So as I look at this guy, again, if I plug the negative 2 in there, 2 to the negative second power is a 1/4, then times the 3 is a 3/4. 2 to the negative first power is a 1/2, times the 3 is a 3/2. 2 to the 0 power is a 1, then times the 3 is a 3. 2 to the first power is a 2, times the 3 is a 6. 2 to the second power is a 4, times the 3 is a 12. Okay? And that one's probably going to be a little bit off our graph, but that's okay. Let's graph the other ones. So negative 2 3/4 is right here, approximately. Negative 1 3/2 is 1.5. That's right here. 0 3 is right here. 1 6 is right here. And then, of course, 212 is kind of off the graph a little bit, but we can kind of imagine where that is. And so we look at this thing, it looks kind of like the other two, except it's steeper. The curve increases much faster, so it's a steeper curve. But then we have to make a judgment call about what's going to happen on the left-hand side. Is it going to do the same thing? Is it going to get closer and closer to the x-axis? And the answer is yes. As we start to think about those values, well, yeah, this is going to get closer and closer without ever actually touching, because there's no values that could make that zero. There's no values that can make it negative, okay? And so I get this steeper curve, but let's talk about those patterns we looked for. The b value being a 2, in the other equation, that was what I multiplied by. Look at this. I went from 3 to 6 to 12. Isn't that multiplying the height by 2 each time? So that's the b values describing the pattern. And look at this, the a value, well, that's the y-intercept right here, okay? And so as our kind of quick form of graphing this thing, because we don't want to do xy charts every time, in this scenario, the a value is like the y-intercept where we start, and then the b value is like what we change the height by, but in terms of multiplication, okay? Along those same lines, if we look for the pattern from the xy chart, here's the first two that we graphed, the pattern is describing the b value right here, look. To get from 1/4 to 1/2 is times 2. This is times 2. I should write the multiplication sign in here. This is times 2. This is times 2. Okay? And so, again, that b value, when we looked at it from the graph, we could see the height increasing. We could see the height of doubling in terms of the y values. Now we can see that pattern within this guy. Okay? And so we see that the b value is the thing we're multiplying by each time. Okay? Over here, same kind of thing. As we look at this, think about it in terms of multiplication. You might look at this and say, oh, it's divided by 2, divided by 2, divided by 2. And that's a great way to think of it when we're looking at the graph. When we're looking at the graph, when we're looking at these heights, we're saying, oh, the y value got cut in half, and then it got cut in half again. And that's great. But when you're looking at it here, think of this as, oh, that's times 1/2. It's times 1/2. It's times 1/2 to get from one point to the next. In terms of the pattern for this, that's the b value, okay? And then once again, hopefully you recognize that, yeah, this was the a value, okay? So the a value is the y-intercept. The b value is what we're multiplying by each time. And that multiplication, that b value, that's the defining characteristic when we're looking at these things and determining if it's an exponential function. So if we're looking at a table of values, we're looking for a pattern that's multiplication. That's how we figure out that this thing is an exponential function, okay? Just like when we looked at lines, remember linear equations, the defining characteristic was that it was a constant rate of change. The pattern we looked for was addition, okay? So to determine if a function is exponential, we're going to check for a common ratio. We're going to check to see if we're multiplying this by the same thing each time. And the reason it says common ratio is we could be dividing by the same thing each time. A ratio is a fraction, okay? So we're basically saying, hey, are we multiplying by a number or a fraction of a number, okay? And so as I look at this thing, we just check and say, okay, what's the pattern? How do I get from one point to the next? And here it's times 3, times 3, times 3, times 3. And so the pattern is we're multiplying by 3 each time. So yeah, this one's an exponential function because the pattern follows an exponential rule. It follows multiplication. And we can take this a step further and say, hey, this is the b value. We can see right here, this is our a value. So yes, this is an exponential function, and it's going to be y equals -1 times 3 to the x. Okay, I can actually write the equation of that thing. So yes, this one's exponential, and there's the equation. If I look at the next one, again, we're looking for the pattern. We're saying, hey, to get from one point to the next, this was times 2, then times 3, then times 4. And so we have a definite pattern here, and it's a pattern in terms of multiplication, but we're not multiplying by the same thing each time. And just like when we were identifying lines, linear equations, we're looking for a pattern that was adding, but it had to be the same thing each time. The rate of change had to be constant. And it's the same thing here. The thing we're multiplying by has to be constant each time. And so no, this one is not an exponential function. Okay? If I look at the next one, once again, I look for the pattern and say, hey, I multiply by 4 to get from 1/8 to 1/2. And then I multiply by 4 again to get from 1/2 to 2. and this is times 4, and this is times 4. So the pattern is I'm multiplying by 4 each time. So this one's an exponential function. And it's an exponential function because it's following that pattern of multiplication, and it's constant. It's a constant multiplication. And I could write the equation. Let's take it a step further. Right here, here's the y-intercept. It's a 2. And then it's 4 raised to the x. And again, that idea that the b value, the thing being raised to a power, is the thing I'm multiplying by, well, that's what exponents are, okay? 4 raised to a power is multiplying by 4 over and over and over again. 4 to the 4th power is multiplying by 4 times. So if we see multiplication of 4 over and over again, that's 4 raised to a power. That's why it becomes the b value, all right? That's why this is described in terms of multiplication. That's what exponents are, okay? If I look at something like this guy, it says 30 beetles are left undisturbed in a warehouse bin. The population doubles each week. The function f of x equals 30 times 2 to the x gives the population after x weeks. And really, what's interesting about this is right now I'm giving you this equation. Well, it would be just as easy for me to ask you to come up with this equation. All right, the idea that we're doubling, that we're multiplying by 2 each week tells me that this thing is exponential, and it tells me that that should be my b value right here. Doubling each week, that means times 2 each week. Well, that's the multiplication. That's the b value. And then the y-intercept is like the starting value. It's where we start from. Well, that was 30 beetles. That's what we started with, so that's the a value. Okay, and so keep that in mind. Here's an exponential equation. We should be able to come up with those exponential equations ourselves eventually, okay, all by ourselves. So now what's the population after 56 days? If we look at this thing, so when we plug this in, students tend to try to do this. They go like this. They say, hey, let me plug a 56 in here. Remember function notation, whatever's in the parentheses, that's what we plug in for x. But they try to plug this 56 in here. And the question is, why is that incorrect? Why can't I do it like that? This is actually wrong. Let me cross it out. And it's because of units, all right? One of the big things with exponential functions is you want to always make sure that the units match. And really that's true for any equation if we're talking about certain units, but especially in exponential functions, because these things will get drastically different if we have the wrong units plugged in here. And so we look at this thing, it says that x right here, x is the number of weeks. So right here, x has to be in weeks. And I just tried to plug days in there. So as we look at this thing, let me try again. 56 days is actually 8 weeks. So I'm going to plug an 8 in here, and now everything will work out okay. All right? And so from here, this is a job for my calculator. Let me grab mine. But when you do this, make sure you follow order of operations. You have to do the exponent first, so 2 to the 8th power. That gives me a 256. I'm going to write the work out. And now do the 256 times the 30. One of the most common mistakes, believe it or not, that students make is they will multiply the 30 times the 2 and get a 60, and then raise it all to the 8th power. You still have to follow order of operations, okay? And again, what's nice about function notation is we see the input-output here. And so input-output, the input is an 8 and the output is a 7,680. So after 8 weeks, it translates into a sentence. After 8 weeks, there are 7,680 beetles. Okay? And as you're looking at that, if you're thinking, man, I only plugged an 8 in and I got a very big value, okay? Students will always second guess these at first because they're not used to values getting so big so quickly. That's how exponential functions work, okay? Exponential functions, if you think back to the graph here, all right? As we think back to the graph, they start off very kind of shallow, all right? They're very close to that thing, and then all of a sudden, they take off. And so as we look at exponential functions, they're neat because they start off with only very slight increases, and then all of a sudden, the increases become very, very large, okay? And that's the idea behind exponential functions, all right? If they're decreasing, the amount that is decreasing starts out very large and then kind of levels off as we get closer and closer to the x-axis, okay? That's when we think about exponential functions from a real-world perspective, that's what we see, all right? It always starts off small and gets big when it's growing, or it starts shrinking very quickly and then kind of levels off and it ends very slowly, okay?